Hi everybody, it's Mr. Neff. Today let's look at the free body diagram practice worksheet. And before we do, did you hear what the pool said to the lake? I'll tell you about that at the end of the video. Now on all 11 of these problems, what you want to keep in mind is if there is no acceleration, then that means that you want to show a net force of 0. And if there is acceleration, maybe there is a positive acceleration, then you want to show a positive net force. And if there's a negative acceleration, a negative net force. So the direction of the acceleration will indicate which direction the net force has to be. Now this, in number 1, the book is at rest on the tabletop. So let's draw the book as a simplified dot, or you could draw a rectangle as a book if you like, and diagram these forces. So it's in the gravitational field, so we'll draw the force of gravity going down. Now, I drew that 3 blocks down. That's an arbitrary number. But now that I have drawn that, I'm going to draw the normal force the same size. Now, I'm using the one vector to judge the size of the other vector. You can also use the grid for that. You want to label that as the normal force. Remember that normal force is the force that comes from a deformed table or surface being bent in and springing back out. So there's the normal force. I can see that since the two of them are the same size, I have no acceleration. Number 2, we have a girl suspended motionless from a bar which hangs from the ceiling. Diagram the forces acting on the girl. So this is a little different than if it were the bar. And so let's do both of those. So let's say this is the girl right here. And I don't know what she weighs. Let's say she weighs 2 boxes worth of force of gravity, like that. And so now she's hanging from a bar. So that it's the bar and it's elastic force that's going to be holding her up. So I'm just going to put this like this. Now I don't really want to call it a normal force because that's not exactly a flat surface. So I'm just going to call it force a bar. It's going up. And she's suspended motionless, so you can see those two are the same. Now if I were to draw the bar's free body diagram, so this is the girl over here, and this is the bar over here. Now, the bar would have its own weight. Let's say it doesn't weigh that much. So force of gravity. It would also have the girl's weight pulling down on it. So force of gravity. But this time, I didn't leave myself enough room. I'm going to call that the force of the girl. When the force of gravity is like for a thing itself. So that's force of girl. And now I have 3 total boxes down, so I need 3 total up. But there were 2 ropes, so each rope is going to get 1.5. So I'm going to go 1.5 up, force of tension there, and 1.5 up, force of tension there. So for this problem, it's probably more like the left picture because it said diagram the forces on the girl. But if you were going to do on the bar, it would be that right picture. In number 3, an egg is free falling from rest in a tree. Neglect air resistance, diagram the forces. So let's say this is the egg right here, and it says it's free falling. Now that's not just chit chat. That's something that means something to us. It's the only force acting on it is the force of gravity. So that's it. Particularly when we're neglecting air resistance. They didn't have to say that, did they? Because free falling means neglect air resistance. Flying squirrel is gliding without flapping its wings from a tree to the ground at constant velocity. Consider air resistance. You have to consider air resistance or there are no flying squirrels, right? Or no flight at all. Diagram the forces acting on the squirrel. So anytime I've seen a flying squirrel, and I actually have seen this before, anytime I've seen a flying squirrel, they're usually going diagonally. This one can't be, and I'll explain why. So if this squirrel is going straight down, then the force of gravity is going to go down like this. Again, that 2 blocks is arbitrary. And each picture, by the way, in this isn't necessarily working with the other pictures. I'm not saying that this squirrel is lighter than an egg. I'm just saying that I just picked 2 boxes for this. Now, I need to show constant velocity, so I have to show no acceleration, no net force. So I'm going to draw the air resistance the same size. I'll call that force of drag, which is what engineers generally call air resistance, and that's showing no net force. So no acceleration. Now the thing is, if the squirrel is going diagonally, then it can't be going at constant velocity, and here's why. The drag force is always going to go exactly backwards from the direction of motion. When you encounter a fluid, it applies a force on you through its pressure exactly backwards. And more on that in physics too. But if this is the squirrel that's going diagonally now, and maybe its velocity, which doesn't belong on the free body diagram, so I'll just draw it over there. Maybe it looks like that. So that would mean that drag force would have to be backwards. So force of drag here. Now I have that same force of gravity, and make these two work together, so draw that the same size as you did before. Now here's the thing. Maybe in the y direction, this component of the force of drag balances the force of gravity. Maybe those two are the same, but you're going to have this x component, and there's nothing to balance that. And so this picture on the right, in the y direction, there's no acceleration, but in the x direction, there is going to be acceleration. It's going to be negative something because of that negative net force. So I guess they didn't mean for you to draw it the way we did on the right, but the way on the right is more realistic. All right, number 5, a rightward force is applied to a book in order to move it across a desk with a rightward acceleration. Consider the frictional forces, neglect air resistance. So we are going to draw the book as a dot like we have been doing. There you go. And it has rightward acceleration. So that means that the net force has to point to the right. Now they say consider frictional forces. Now frictional forces acting on something sliding across the desk are going to act parallel to the desk and backwards in this case. So maybe this is an applied force, a catch-all term for force of a hand pushing or something like that. And then there's going to be a frictional force back here like this. We generally call this force of friction. Now, as we get into friction, we're going to see there's two kinds of sliding friction. Static, which is the force that's actually holding two surfaces together with no relative motion, and then kinetic, the one that is just resisting the motion as it's one sliding across the other. We really have the book sliding across the desk, so it's going to be kinetic friction. Now, there's also a force of gravity on this book, like so. And there's also a normal force on this book. There you go. No acceleration in the y direction because no net force there, but there is acceleration in the x direction. It's positive acceleration, and you can see the positive net force. 6 is similar. This has a book that is moving with constant velocity. I'm going to make it the same book. So I think I drew 2 boxes of force of gravity before. I'm going to draw 2 boxes of normal force. That's exactly what I had before. But now this time, I'm going to have maybe 1 box of friction, and that means I have 1 box of applied force. The arrow is shorter. I'm not pushing as hard. This has no acceleration in the x direction now. This has no acceleration in the y direction. It has no net force. College student rests a backpack upon his shoulder. The pack is suspended motionless by 1 strap. Diagram the vertical forces acting on the backpack. Maybe it's got a lot of stuff in it, force of gravity, and since it's coming from a strap, I'll call it tension, same size. Skydiver, descending with a constant velocity. You'd need air resistance just like we did with the squirrel. Diagram the forces acting on the skydiver. Now, here again, if it's the skydiver themselves, then there's going to be probably 2 tensions going up on the skydiver and balancing out the force of gravity. So I got 3 boxes of force of gravity going down. And how about maybe a box and a half up and a box and a half up at the same angles, because you've seen the skydiver before. Here they are, and they're going to have, you know, the strings coming up to the parachute. So this will be a tension, this will be a tension. You can see what I'm trying to draw here. I've got an X component and a Y component on each one of those, and I'm trying to show the X components canceling out and the two Y components together adding up to balance out the force of gravity. So that would be for the skydiver. Now, if it was the skydiver parachute system, then I would have more like this. Now, this parachute doesn't weigh much, but it weighs a little bit, so I'm going to draw the force of gravity a little bit bigger. And now I would just draw the air resistance going back on the whole system, something like that, and I would call that the force of drag. Okay. Constant velocity. Now, a lot of people would say, oh, well, if the forces are balanced, does that mean the skydiver is not coming down? No, that just means that the skydiver is just maintaining whatever speed they had whenever they got into this state. 9 says a force is applied to the right to drag a sled across loosely packed snow with a rightward acceleration. Diagram the forces acting upon the sled. Now, most of the time when you pull a sled, you pull it sort of diagonally up like this, so we'll call it force of tension, thinking that you're going to use a string to pull it. And so here's a force of gravity like that. Now, there is a X component that's going forward, force of tension X, and it's snow, so I don't know if they assume that we should assume there's no friction, but I'm going to put a little bit of friction on this. Force of friction kinetic again. So I still have a rightward acceleration. Now you see something too. There's two boxes of tension going up, force of tension Y, but there were 3 boxes of force of gravity going down. That means that there has to be 1 box of normal force, the ground, pushing up. 10, a football is moving upwards towards its peak after having been booted by a punter. Neglect air resistance, diagram the forces acting upon the football. Well, aside from the air, which we're neglecting, the only thing that the football is touching is the gravitational field. So it is a projectile. Someone might say, but it's going up. And I'm going to say, well, it's only going up because it was going up. It's actually on its way down because it's being accelerated down. Velocity is something like this. The only forces that are acting on it are the force of gravity. And no, we don't have this force from the foot on there. We did while it was being actually kicked, but now it's gone, and so that force is gone too. Here's a car coasting to the right and slowing down. Diagram the forces acting on the car. Now, if our velocity is to the right, but we're slowing down, then that means our acceleration must be to the left, and so our net force must be to the left as well. When a car is driving, you're pushing on the gas pedal, you often have a force of thrust going forward. So, but here we're coasting, so that force of thrust is not there. Instead, we have a force of gravity going down, we have a normal force going up, and now we have some resistive forces. Maybe some of it's air resistance, maybe some of it is rolling friction with the road. And so we're just going to call that force resistive like this. I would be okay if you called that friction too, force of friction, or even if you call that force of drag. There's a lot going on whenever a car is moving. Anyway, I have nothing going to the right because it's just coasting to the right, moving forward still because of its inertia, and the acceleration is backwards. All right, so I hope you saw a lot of first law and second law in that worksheet, and that you're able to draw the free body diagram and set yourself up nicely to solve. Before we go, what did the pool say to the lake? What are you doing here?